Hello everyone. Today we are going to learn about triangulations and its theory. So let's start with the control points, or you can say control surveying. So what is control surveying? So control surveying is the determinations of the precise positions of a series of stations distributed over an area to serve as the origin or reference to be used for checking of subsequent surveys to be used in engineering projects like property delineations, topographic and hydrographic mapping, and constructions planning and design. So control networks which cover the whole country have become been conducted with better accuracy and less stringent technique with the use of artificial satellites. So these stations are linked to local networks which have been adopted for special surveys connected with the projects such as you can say dams, roads, railways and pipelines, or also large or small construction site. So the purpose of a control system is to prevent the accumulations of errors by connecting detailed work to a consistent geometrical system of points which are accurate enough for the project. So great care is taken to ensure that this control is sufficient to accurate. Here you can see the figures showing the networks, local networks. Uh, so linked with the linked with the control networks, so you can get a better ideas. So this is a building one, building two, three, fours, and this is a plain area. These are the roads and these are the points taken. So you can say these are the control points. Now, let's get the definitions of control surveys. So, this is basically conducted to establish a system of horizontal and vertical control points over the area to be mapped. So, what is a horizontal control point? So, here you can say that I write here that horizontal control points can be established by different fill methods such as triangulations, trilaterations, traversing, and using GNSS receiver. And vertical control is usually accomplished by leveling. So let's get some more deeper definitions about triangulations, trilaterations, and what is the towers and what is the GNSS. So triangulations, that is, the terrain is divided into well-conditioned triangles whose angles and lengths of baselines are measured correctly, or you can say accurately. And in trilaterations, the lengths of sides of the well-conditioned triangles are measured very accurately. So in traverse, both lengths of sides and angles of the well-conditioned triangles are measured very accurately, while GNSS, that is a global navigational satellite system, such as you can say that GPS, GLONASS, etc. So the receivers of these systems provide the positions of control points and the azimuth of the lines directly through field observations and processing of software. So now let's focus on triangulation, or you can say trigonometrical survey. So in triangulations, generating a control network by means of a network of triangles. Okay, so networks of triangles in which only base length we measure, and we measure all other angles of that networks of triangles, and with the help of this we can compute all other lengths or networks of that triangles. So base length we can extend a small into the bigger one. So types of figure used in triangulations that play a major role in this system. So there are various types of figure used in triangulations, like a chain of triangles, or a chain of quadrilaterals, or centered figures. So in practice, actually we will be using combinations of these various figures depending what the terrain is, what is your applications, and what is the area which are, or which we need to map. So let's take a look on this figure. So you can see this. I draw some random networks of triangulations. Here, this is my non-baseline that may vary small to bigger. So I design a network of triangles. See, one triangle, here is another, here is another triangle. So what is that? In this figure, see, we know the, that means that this is the non positions, this is also non positions. We also have a baseline, means we know or measured baseline, or these all angles are measured angles, and with the help of this baseline and measured angles, okay, see, you can see this is a measured angle, this is a measured angle, this is also measured angle, measured angle. So with the help of this all measured angle, we can calculate the distance. Okay, so that is what a city means. City means calculated distance. So we can calculate this distance and this distance, all distance we can calculate it, and also this positions. Okay, calculated positions, we can also calculate the positions of that points. So this is one fundamental, you can say that this is only for the understanding purpose, this figure. So baseline we know, and measured angle we know. From that too, we can calculate the distance of other sides of the triangles. Now let's start with the shape of a triangle. Here you can say that let's start. This is my baseline. Okay, I draw one network of triangles here, one here, one here. Okay, suppose I extend this triangle to here, and I extend to this here, extend again this to here, and again this to here, and say somewhat like I'm extending this network of triangle here. So in this figure, you can say this here is our baseline. So I denote this point as a B, and C. So these all pointed where I thought. Okay, so these are all pencil dots are my measured angles. These are my measured angles. Okay, so this is the baseline. Suppose this is the baseline. Okay, and all these are measured angles. Now if I want to find out this length, or if I want to find out this length, or all other sides of the triangles, if I want to find out, so what I have to do first, that with the help of baseline and measured angle, I have to follow the roots. So this, so baseline is known, measured angles are known. So what I have to do for finding this length, I have to following the roots. So roots may be like this way. Okay, so I have to follow the rules, and by following the routes I can find out the coordinates or the lengths of the other sides of the triangles. Okay, so this is a triangulation system what actually going. So suppose, let me clear a very more easily and convenient way, that if I can say that this is a baseline, I know. Okay, so let, this is the distance C, and this length will be distance B, but I don't know what is the length of B, but I know the length of C. So in this triangle, by following the sine rule, okay, so what is the sine rule? So let me clear here that if I want to find out this length, so B equal to C, so length of this baseline into sine B divided by sine C. So this is the sine rule. By using the sine law or sine rule, I can find the length of the B. So this may contain some errors. Okay, so effort of error is minimum, you can say, when we get effort of error minimum when shape of triangle based shoot. Now the question is that what is the best shape of triangle that should. Okay, so before going on to that topic very deeply, let's see some shape of triangulation, that this shows single chain of triangles. You can see the triangles in a single chain. Now this is the double chain of triangles. Okay, so one here, one another here. So one chain of triangle is upper side, one chain of triangle is bottom side. Now this is like a centered figures shape of triangulation system, and this is a quadrilaterals. Okay, so our question is that if we want to minimize the error in to find out lengths or coordinates of the other sides of the triangulation system. So, what is the shape of triangle that best should? So, let's focus on that. So, for minimizing the error in means a length or coordinates, you can say that we have to find out the base shape, and that means a well conditioned triangle. So there are various triangulations figures, and accuracy attained in each figure depends upon, I can say that the magnitude of the angles in each individual triangle and the arrangement of the triangles. So regarding the shape of the triangle should be such that any error in the measurement of angle shall have a minimum effect upon the length of the calculated side. So such a triangle is then called well conditioned triangle. So let's find if I have a one curved line here in another that is making a message very small angle. So this you can say that if I double, let me make a more thicker line so you can get the actual idea what I want to tell you. Suppose see, this is the thickness of the curve line. Okay, so this is one curve, so this is one curve, okay, thicker, and this is the another curve line. So area of contact, you can say the area of contact, I make a triangle, so let's make a triangle. So this is the triangle, so there will likely to have a more errors. Okay, but if I make an angle of 90 degree, so let's make, this is a one, let's make a line more thicker, so this is one line, and if I cross since a 90 degree, so the uncertainty of John is very small. Okay, so error will be less when we are making a angle of a 90 degree, and other than that is maximum. So hence the base of triangle is with the base angle equal to, you can say that 56 degree and 14 minute. However, from practical considerations, an equilateral triangle is the most suitable. So in general, however, triangles having an angle smaller than 30 degree or greater than 120 degrees should be avoided, and other angles are preferred. So what is the uh, error for the error? So let's again as described earlier that the by sine formula, let's start with b is equal to c sine b by sine c, that is by sine formula we got this. So from this figure, let's start with that the AB, the non-sides, and BC and CA with the sides of equal length to be computed, and evidently angle A and equal to angle B. So by the sine formula for this triangle, we can say that B equal to C sine B divide, B equal to, or this is, sorry, this is wrong. So by sine formula, you can say A equal to C sine A divided by sine C for this. Okay, now let assume delta A. So error in measurement of angle A, and delta A1, that is a corresponding error in side A. So and differentiating a partial, we get this equation. So what we can get that, let's write here, delta A1 is equal to C cos A into delta A divided by sine C. So again delta A1 divided by A, we can find that cos A divided by sine A delta A equal to delta A into cot A. So similarly, we can find out delta C and delta A2, okay, by the same procedure. So I'm writing here directly. So I am writing here directly that delta A2 equal to minus C sine A cos C delta C divided by sine square C. Okay, so therefore delta A2 by A we can find minus delta C cot C. So if delta A and delta C probables errors in angles, and that could be delta and plus or minus beta. So the probable fractions error in the side A, we can write that probable fraction error in the side A be beta under root cos square A plus cos square C. So this is minimum when cot square A plus cot square C is minimum, obviously, but we have problem that C equal to 180 minus A minus B. This is from the triangulation. We can say that sum of all the angles of triangle, that is 180. So 180 minus 2A. This is a simplifying. So that's for cot square A plus cot square 2A should be minimum. Okay. So definiting cot square A plus cot square 2A with respect to A and equating it to 0, we get after reductions that 4 cos square A plus 2 cos square A minus 1 equal to 0. So by these equations, or you can say from which we find out A is equal to 56 degree and 14 minute approx. So as earlier I am saying that the base shape of triangle is isosceles with the base angle equal to 56 degree and 14 minute. However, from practical considerations, an equilateral triangle is the most suitable. So we have to always remember that angle smaller than 30 degree or greater than 120 degree should be avoided. Thank you.